All right. Let's take a look at our first lesson in Unit 6. I know this is, I'm pretty excited. We're actually going to be looking at integration. Unit 6, we'll just look at this, is our integration unit. We're going to learn how to integrate. So the first thing we're going to talk about is just basics like area under the curve. So let's look at this right here. All right, so area under the curve, you may or may not have heard that term before. That is basically one thing or one, I don't know, what shall we say? It's one aspect of integration that's important. And so this would be like the geometric aspect of like an area under a curve. This is how we would think about it geometrically. And so the area under the curve is the region, it's the region between the x-axis and the function. That's what we need to keep that in mind. It's between the x-axis and the function. It's not necessarily like underneath, like below. It really depends on where the function resides. Where is it? So we're looking at the region between the x-axis and the function. So the fancy word here is that the area under the curve, if we're using a graph of a rate of change, which we do frequently, the area under the curve gives us the accumulation of change. And you don't really need to completely understand what I'm talking about, but that's just this is where this area accumulation comes in. We're actually accumulating area as we move. Typically, we move from left to right. So for our first example, we're just a basic example of, we're going to highlight the area under the curve for each of the graphs so that we can really understand exactly what this is referring to. So what I would do is I would highlight this area right here, and I'm going to stop at the x-axis. Okay, so we're going to stop at the x-axis, and if my graph looked like this one, that's what I would do. That's how I would highlight the area under the curve, which is kind of straightforward. What we need to take note of is that it actually stops at the x-axis. Okay, so it stops here. We're not allowed to go, on the other side of the x-axis. On the second graph, you can see that it actually the whole graph resides underneath the x-axis. So when we do we're just going to put that in quotes, area under the curve, it's really not underneath this. It's actually, we want to focus on the fact that it's going to be the area between the curve and the x-axis. So with this scenario, what we would do is we would highlight this part right here. This would be, although I know it's not, it's technically not underneath, but this would be the portion that would be the area, under the curve. It's the portion between the curve and the x-axis. Okay, so that's a second scenario. Then the third scenario is actually a bit of a mixture. If you can see, it's doing, it's going crazy. So for this one, this portion right here would be, we would, highlight that. And then this portion right here. So again, we're looking at the area between the graph and the x-axis. So these are the areas that we would be talking about. Like the third one is just a hodgepodge. It's going above and below. It's being crazy. But bottom line, the area under the curve is between the curve and the x-axis. So why is that a big deal? Well, the reason it's a big deal is, let's say let's just call this f of x. Well, just for fun, we'll call it f prime of x. If I was integrating f prime of x between -1 and 1, 2, 3, 4, 5, we'll just call that 6. This would be the integral that would find the exact area under the curve. Okay, that's basically what we're looking at is what does the area under the curve represent? How does that tie to integration? Dx. I'm going to use a different color to make it more clear. So this would be dx. And I'm going to go into all the parts of that in a moment when we get to that page. So that's just what our integral, well, that's what this is. Calculus. This calculus right here is what this calculus would do is it would actually calculate the area under this strange looking curve, and it would do it exactly. Unlike in geometry, you know, we can only do area with, like, I don't know, specific shapes like triangles and squares and semicircles. With calculus, we can do the area under anything. That's one of the powers of calculus, is that we can do the area under anything. So that's the concept that we're going to be talking about basically in this entire unit. So that's the first question. Now, before I go to the second question, I want to make note of this little note right here for units. So units for area under the curve. So what we do is we take the dependent unit, which is, you know, y. Y is the dependent unit, and we multiply that by the independent unit, and the independent unit is, you know, x. Normally x and y. In other words, we take the unit for y and multiply by the unit for x. That's how we come up with the units for area under the curve, is we're going to multiply the units for the y values with the units of the x values. And I'm going to show you how that works in number 2. We're going to talk about and we're going to work through that unit issue, units for area under the curve. So on number 2, they're asking us, say we're on a road trip and we have your cars on cruise control for 4 hours. You travel at 60 miles per hour. How far have you traveled? Okay. So basically, here's our miles per hour. Here's how fast we would go. Here's how many hours we're driving. If we are driving 60 miles an hour, which is this dark line right here, for 4 hours, basically this would be this portion right here. This would be the area that we would need to calculate. Okay, now it's just a rectangle, so we don't really need calculus to calculate this. But, so what would we do? Exactly. We would do 60, and let's put the units with it. We would do 60, and that's miles per hour. And I'll just write out the words, miles per hour. And we will multiply that by 4 hours. And when we do that, you probably remember from your science classes how these units, like what's that called, dimensional analysis in science, where those units would go away. And then we would be left with 60 times 4, which is what, 240. And our units left would be miles. So when I first learned this, it was very strange for me how area could be distance. I don't know if that troubles you or not, but it troubled me a great deal, how the area under that curve could actually turn into distance. And so what helped me come to terms with that is, you know, like, I don't know which math class, but it was long before calculus, we learned this distance equals rate times time. Remember that formula from, I don't know which math class, maybe even middle school, I don't know. Distance equals rate times time. Look how this is the rate and this is the time, and the distance is multiplying those together. So that actually connects to something we've done before. It connects to this formula, distance equals rate times time, because that's exactly what we're doing. Does that make sense? Okay. And so right now what we're looking at is the overall concept of area under the curve. That's what we're working on right now. And number 3 is the third and last example of this overarching concept of area under a curve. So what we have now is you've got the graph to the right represents the rate at which the water is leaking out of a tank. Okay, so here is our rate right here. And the rate is in gallons per minute. Okay, how much water has leaked out of the tank after 9 minutes? And here's our minutes, and that would be 9 right there. So the quantity, I want you to refer to this right here. When we were looking for the distance, what did we do? We multiplied the rate times the time, right? Here we're looking for the amount of water that's leaked out. We're going to multiply the rate times the time. That's what we're going to do. And so we're actually going to calculate this area under the curve, all of this right here. We're going to work on this. These are geometric figures, so we don't need to use the calculus techniques which you're going to learn. This is just geometry. So what I would do to find that area is I would break this into different pieces. That's what I would do. So I would probably break it right here. So I know that's like 2 times 2 is 4. So that area is 4. And let me make that a different color so it shows up better. This is 4. And it's still not showing. Here we go. That's 4. Okay, and then I would probably break it right here. Again, this is just one way to do it. You can break it a bunch of different ways. I'd break it here and here. Is probably what I would do. And this is what, 1, 2, 3, 4. So 2 times 4 is 8. That would be 8. Then this one is a semicircle, so that's half pi. Let's see, radius would be what, 2 half pi r squared, which would give me what, 2 pi. And this one is a triangle, which is what, half base. The base is, what is it, 1, 2, 3 times the height, which is 2. So what is that? That's 3. Okay. So we're going to add up those numbers. That's going to represent the quantity, the amount of, what are we doing? Water? The amount of water that leaked out. So I've got 4 plus 8 plus 2 pi plus 3. Let's see, what does that give me? 8, 12, 15. So that gives me 15 plus 2 pi. And they didn't ask for a decimal approximation, so I'm not going to do it. I'm just going to leave it like that. It's 8 plus 2 pi gallons. And we're going to say the explanation. So the explanation is 15 plus 2 pi gallons have leaked out of the tank after 9 minutes. They love it when you repeat back what they say. Bless you. They love that. I want you to compare what we said with the prompt. How much water is leaked out of the tank after 9 minutes? 15 plus 2 pi gallons have leaked out of the tank after 9 minutes. They love that. Okay? All right, so that's an overview of area under the curve. How are we feeling about that? Are we okay? Okay, so now let's go to the second part of the lesson, which is antiderivatives and integration. Okay, so one use, there's a lot of uses. One use of integration is area under the curve, and that's what we talked about. Calculating area under the curve is one thing that we do with integration. All right. So let's look at these formulas. And what I want you to do is I want you to think, so I know you're probably pretty excited about learning a lot of new formulas, but really what I do is I think backwards. That really helps me. I don't really want to learn a lot of new formulas. So what does that mean? That means that I'm going to think about, let's see, for instance, I'm going to think about natural log. I'm going to think about what is the derivative of natural log? It's 1 over u, right? Isn't that the derivative of natural log is 1 over u? Right? Look, the integral of 1 over u is natural log. See how it's backwards from what we've been doing? It's backwards. Please make note of that. And I wish I could tell you that we're only going to be doing integrals and so you'll never get them mixed up, but we're not. We're going to be going back and forth constantly between derivatives and integrals, and you've got to keep it straight. Okay, so I would think to myself when I am thinking about trig, I would think to myself, what what did I take a derivative of to have gotten a positive sign? What in the world would I have taken a derivative of to have gotten a positive sign? Well, I would have taken the derivative of a negative cosine to have gotten a positive sign. You with me? That's how I think about integration, these integral rules. I do not relearn everything. That is too much for me. But y'all are great at memorizing. Maybe you want to memorize all of them from scratch, but I don't. I want to go backwards. Okay? So that's what I would recommend you do. And in calculus, e to the x is our friend. I mean, the derivative of e to the x is e to the x. The integral of e to the x is e to the x. How much easier could you get? How much easier? Not very much. Okay, so these are new formulas for us. I want to talk about integration specifically, so I want to come over here at this text box and talk about it. So the process of taking an antiderivative is called integration. That's what integration is. It's the process of taking an antiderivative. Okay? And so we've got two kinds of antiderivatives. We've got an indefinite integration. Indefinite integration means there are no bounds on the integral symbol. It's like that. It's just like that. That's indefinite integration. It's just the integral symbol. And with all indefinite integration, we have to use the constant of integration c. We'll talk about that in great detail. But I just want to highlight that. I'm highlighting it because for some reason it's forgotten a lot of the time, and that will be bad. So we use a symbol to represent an antiderivative. It's called the integral sign. It's this little curvy thing that I'm drawing. That's called an integral sign. And the equation that we write, the integral is written like this. It would have an integral sign, and then it would have the function, whether it's f or f prime, whatever. And then it has the dx. Okay? The dx confuses students for some reason. What does the dx do? It tells us which variable we're integrating. And it also tells us when to stop. So it's really important. The dx is really important. It tells us the integral that we're integrating, which we're doing single variable calculus. So, I mean, it would just be one integral, one variable. And it also tells us when to stop integrating. It's our stop. And I'm going to circle this, and I'm going to put a big asterisk around it. So that's the most important part of the dx, is it tells us when to stop. If you don't put it, you're in danger of losing points because you're not saying when to stop. Now, you may know when to stop and stop properly, but I'm just saying it's dangerous. We need to put it. Now, the notation that a lot of mathematicians use, if you integrate little f, the actual antiderivative is big F. That's not required. It's just a common notation. It's just common. And notice we've got the plus c. This is required. Plus c is required. Okay? You can't not put it.
What is a plus c?
So I'm going to show you out to the side why we have a plus c. I'm just going to say, let's say our original function is 3x squared plus 2. Okay, let's say that's our original function, and we want to take the derivative. So when we take the derivative, what's the derivative of 3x squared? It's 6x, right? And the derivative of 2 is 0. All right, let's say we want to go backwards. We want to find f of x. And we want to do the integral of 6x. Right? This is going backwards. And this is the reverse. I call it the reversal power rule. I don't know if it has a name for it. So what did we do when we did this derivative? We took the 2 and we subtracted 1, right? First of all, we multiplied it. We multiplied the 3 times 2 and we got 6. And then we subtracted 1, right? That's what we did. We multiplied, then we subtracted. That's what derivatives do, right? Okay, antiderivatives, we're doing the opposite. Instead of multiplying, we're going to divide. And instead of subtracting, we're going to add. So on our antiderivative, we're going to divide and subtract. Oops, and add. We're doing the opposite. So this is a 1. So I add 1 to 1 and I get 2. So that gives me x squared. And I divide by 2. So that gives me 3x squared. I don't have anything else. But what was this? Isn't this important? Right here? Isn't that a big deal? Yeah, that was a big deal, right? So that's why we have the plus c to allot for that number. Are you with me? It's really important because if you don't put plus c, so f of x in this case would be 3x squared plus c, and I don't know what the constant is, I would need more information. That's why we need the plus c, is because when I take the derivative of a constant, it goes away, it disappears, and I need to account for that in my work. Does that make sense? Okay, that's why you will lose a point if you don't put plus c in your work. You just will. And you're not going to, I had a student count up the number of, it's been crazy. I've had a student count up the number of points they lost because they forgot to put plus c. It was astronomical. And I've had students write at the very top of their paper, gigantic, like plus c, like, I don't know, like 5 inches tall. And the very first question was an integral and they forgot to put plus c. I don't know why this happens. I just don't, it's a mystery. Please don't let that happen to you, okay? Put the plus c. Put the plus c. Okay. All right. So bounds or no bounds. I've talked about that briefly. I'll talk about that again. So a definite integral will have bounds like a to b. An indefinite integral will not have bounds. That's just the difference. And we'll get into more specifics about that later. The indefinite integral needs the plus c. The definite integral does not need the plus c. There, we do something else with it. Does not need plus c. Okay, so now let's do some antiderivatives. We're now just think about going backwards from what we've been doing. Okay, we've got, I think, I don't know, 3 or 4 examples. What do we have? We have 6 examples of antiderivatives. Okay, and then that will be our lesson. So the first one, if f prime is e to the x minus 2x squared, find the particular solution. So before we do particular solution, I actually want to do a general solution. Let me find a, let's do this one first. Okay. So when you look at that, I'm hoping you recognize that derivative, because if you don't recognize that derivative, you're not going to know what to do. Does anyone recognize which derivative this is? It's arcsine. This is arcsine. If you don't know it, you're going to be in a world of trouble. Okay? This is arcsine. So if this is the derivative, so if I do the antiderivative of this, I get arcsine of x plus c. I mean, that's my answer. There's nothing else to do. Okay, that's an indefinite integral where I don't have any additional information. If I don't have additional information, I just put plus c and I'm done. Yes. Yes, because this is the literal formula. So yes, this would be on a formula quiz. Okay. So now let's go to one where they give us additional information. And the reason they give us additional information is so that we can find the plus c. Okay, this part here is additional information so we can find c. I mean, that's what it's for. Okay, sometimes they give it to us, sometimes they don't. It's okay. And when they give it to us, they call it, this is the words they use, they call it the particular solution. The particular solution. Why do you think they call it a particular solution? Could there be more than one solution? Could I have more than one c? Let's think about this for a second. If I didn't have that additional information, let's look at this example I did over here. What if f of x was 3x squared minus 5? Is that going to give me the same derivative? Yes. The derivative of 3x squared minus 5 is 6x, right? It's the same. And if I do the antiderivative of it, I'm just going to get the 3x squared. I have to leave this, so this, it would be a different c. That's why it's called a particular solution, because there's an infinite number of solutions possible. Because there's an infinite number of c's that you can have. So I just want to be clear on these words. All right, so we're looking for the solution where f of 0 equals 4. So here we go. So we're going to say f of x equals the integral of e to the x minus 2x squared dx. Why did I put the dx? Because that's my stop, right? I'm going to stop integrating right there. Okay. So the antiderivative, so f of x is going to be, the antiderivative of e to the x is e to the x. We love it. Okay, I love it. This one, this antiderivative, we're going to have to do the reversal power rule on it. So let's think about that. Okay, so I'm going to have to add 1 to 2 and get 3. And what do I do with the 3? Do I multiply or divide with it? I divide with it. So it's going to be 2/3 x cubed plus c. Okay. So this 2 is this 2. That's the same 2. I added 1 to this 2, and I got 3, and I divided by the 3. Okay? So that's the reversal power rule. I'm doing the reverse of a derivative. I'm reversing my work. Okay, so now we're going to use this information to find c. So I'm going to, y is 4, so 4 equals, we're going to put a 0 in for x, e to the 0 minus 2/3 times 0 cubed plus c. I'm going to find out what c is. That's the purpose of that point that they gave us, the additional information, so we can find c. Now this is dangerous. We put 0 in, we just think everything disappears, right? But what is e to the 0? 1. So not everything disappears. Be careful. So I have 4 equals 1 plus c. So I solve for c, and I get c is 3. Okay, so now let's fix our particular solution. It's going to be f of x equals e to the x minus 2/3 x cubed plus 3. Okay, so I want to pause here for a moment. How are we doing? Okay, we okay? So we found our particular solution by using that point in our general. So this is called a general solution. This is called a general solution with the plus c. Okay, this part right here is the general solution. This is called a particular solution. Okay?
So if it didn't ask for the particular solution, you could just for that.
That's exactly right. We would be done when we put the plus c, we'd be all done. Okay, are we okay on number 4? Yes? All right, let's look at number 5. Okay. So here's what is going to be important for us to recognize. Okay, this one, 3, if I took the derivative of something and got a 3, what would I have taken the derivative of? 3x. So the antiderivative of 3 is 3x. And those are the questions I ask myself all the time. If I had taken the derivative of something and then gotten 5 over x, what would I have taken the derivative of? Natural log of x. Now, it has to be absolute value. I'm just going to say, when we're doing derivatives of, ln x, it doesn't have to be absolute value, but when we're doing antiderivative, it does. Okay, so that's this. These two look the same. They are so different, but are completely different. Okay, completely different. Because if x is to the first power like that, 5 over x, it's natural log. If x is to any other power, then it's not natural log. It's a reversal power rule. So I'm going to do scratch work over here. Scratch work is right here. And I'm going to rewrite, I'm focusing on this one right here. I'm going to rewrite that as 7x to the negative 2. Are y'all okay with that algebra? 7x to the negative 2. So, okay, so I'm going to do my reversal power rule here. I'm going to add 1. When I add 1 to negative 2, what do I get? Negative 1. And I'm going to divide by negative 1. 7 divided by negative 2 is just negative 7, x to negative 1. This is the antiderivative of 7x to the negative 2. Are you with me? So I would write that up here as negative 7 over x plus c. Okay, how are we doing? We okay? Okay. So we've already done number 6. So let's look at number 7. Here's another particular solution. Okay, so here's our additional information to find C. That's what it's for. That's why they're giving it to us. So f of x is the antiderivative of 1 minus sine x dx. Okay. So here we go. F of x would be, what's the antiderivative of 1? X. The antiderivative of 1 is x. If I took the derivative of something and got a negative sign, what would I have taken the derivative of? Cosine, a positive cosine, right? That's what I would have done. See how I don't remember any new rules? I just use my old ones. I really recommend you do that. So if I was, this is the general solution. If I didn't have that additional information, I would stop. But I do. So I have to find the particular solution. All right, so in place of f, I'm putting the pi minus 2 equals x, and this is pi, so pi plus cosine of pi plus c. Yes. Stop. It means that's where you stop in, or you just stop there. And the other use is it tells you which variable you're supposed to be integrating.
So if you're using y's, do y's?
That's right. If you're using y, it would be dy, and then I'd put a y here instead of an x.
Okay.
Yep. All right, so if I move the pi over, it goes away, right? So that's gone. And we know cosine of pi, we know what that is, right? Our unit circle? It's negative 1. So c is what? Negative 1. So our particular solution is going to be x plus cosine x minus 1. So that's our particular. And our general solution has the plus c in it.
Question after the test, do we need to include both the general and the particular solutions, or just the particular?
Just the one they ask you for.
Okay.
Just the one they ask you for. If they want the particular, that's the only one you need to include. Okay? All right, 2 more questions. We're just doing more examples of the same kind of stuff. We're still just doing antiderivatives. Are we okay? All right. So let's look at number 8. This is in fraction form. We are going to learn a rule called it's called the quotient rule, but even if you knew the quotient rule, which we don't yet, you still would want to rewrite this. Rewriting is our best friend. We would want to rewrite this because as it's, as we see it, that we couldn't do anything with it. So what am I going to do? I'm going to turn this into 3 different fractions. I'm going to do algebra. Algebra first. I'm going to rewrite. So 3, and I'll do all the steps. I would typically do that in my head, but I'm going to do all the steps for you. So I do 3x squared over x plus, I would do x over x minus, I would do 2 over x dx. Okay, I'm just splitting it into 3 different fractions because this is a monomial. It's one term. If this were a binomial, I could not do this. That's an algebra thing. That would be bad algebra. All right, so let's simplify that. So 3x squared over x would just be what? 3x. And x over x is 1. And then there's nothing I can do to fix 2 over x. All right, now we're ready to do our antiderivative. So this first one, we're going to do the reversal power rule. My exponent is 1. I add 1 to 1, and I get 2. So I divide by 2. So 3 halves x squared. What's the antiderivative of 1? X. What's the antiderivative of 2 over x? Yep, minus 2 ln x. Absolute value ln x plus c. And we're done. Okay. Last one. So that's a fraction. It's a quotient. We are going to learn the quotient rule, but again, this is way easier if it's possible. This next one is a product. We will learn the product rule, but again, if you can avoid it and it's easier, why not? We're going to rewrite here because we don't know the product rule anyway. We're going to distribute. We're going to do algebra. We're going to do algebra. Okay? 3x times x to the 1/2 is 3x to the 3/2. 3x times x squared is 3x cubed. So that's just algebra. We okay? Does everybody understand where I got the 3/2 from? Right? When I add, so if I add x times x to the 1/2, if I add common bases, what do I do to the exponents? I add them, right? That's algebra. 1 plus 1/2 is 3/2. You with me? Okay, so now let's do our antiderivative. So I add 1 to 3/2. 3/2 plus 2/2 is what? 5/2, right? 3/2 plus 2/2 is 5/2. Dividing by 5/2 is the same as multiplying by 2/5. Plus, I add 1 to 3 and I get 4. And then I divide by 4. Okay, let's clean that up. We get 6/5 x to the 5/2 plus 3/4 x to the 4th plus c. Yay, in our very first lesson on integration. How are we doing? We doing okay?